Hello everybody. So today I would like to talk about graphs, and of course I would also like to excuse me, say a little bit about the relationship of graphs with respect to mathematical modeling. We will see graphs are the skeleton of a mathematical model. You can always define or find a graph that builds up the skeleton of a mathematical model. Whether in a good way or a bad way, we have to discuss. But in that respect, graphs are of course the basic tool for so-called relational modeling. And at the same time, this is also called structural modeling in our language. Okay, so let's start. I give you now the basic graph definition. So let's go through that. A set theoretic structure G of a set V, a set A, S and T. S and T are functions, mappings, as we will explain in a moment, consisting of two sets V and A, called the set of vertices and the set of arrows, respectively, and two functions S from A, mapping from A to V, and a mapping T, mapping from A to V, called the source, and the target function is called a graph. Now, most of you who have already seen graph theory will be familiar with the first two parts in the argument of a graph, and that is the vertex set V and the arrow set capital A. But maybe you haven't thought about two mappings S and T. This introduction of the mappings S and T of this source and target function is very convenient, as we will see, for many purposes, and that's why we would like to introduce that. So let me just briefly say something about the idea of these mappings. As you can see, S here maps from A to V, and that is an arrow then is associated with its source. This is where the arrow starts, and that is a certain vertex in V. So source of course means there is an arrow starting at a vertex V mapping somewhere, but where does it map to? Well, this is then given by the target function T. And this says, where this particular arrow in A is mapping to a vertex in V. Okay, I think that all makes sense. So let's go a little bit to the discussion why such graphs are so important. Well, they deserve a special attention as they are used intensively in mathematical modeling. They are used, even intuitively, even if people are not, even if they are not working inside graph theory or have much knowledge about graph theory, they still would, even in textbooks in other areas, for example in economics or even in sociology, they would use graphs intuitively to somehow illustrate a certain working of a certain system which is relevant in this part of science. So they are used all over the place to illustrate the structural concept of the system. Now I give you an example of a general graph, and that is using a table notation. So you should see that there are different ways how the information that you see in a graph, if it's drawn, just on on paper how this how this information is put into working in different ways. So one way is definitely to draw tables. So here, for example, in the first table, you have a list that goes through the different arrows in an example graph. Here we assume we have here seven arrows, and then we have here the values of the source function for each arrow. So for example, arrow 1 would start at v1, arrow 2 would start at the vertex v3, and so on and so on. And then here in the next table we have just a complete listing of the vertex set v, which contains 8 vertices in this example. And if we draw this, then the result would look like that. And this information, as you can check, is exactly the same information we have for the tables. So you would see that there are 2 components. We will discuss that in a moment of this graph. So the entire graph here is not entirely connected. So there are 2 components which are separated here. This would not, I'm just pointing that out because you might not have seen that so easily in the table. So in this case, the drawing of the graph is making this point much more illustrative. Actually, if you look very close to it, there is a third component just consisting of 1 vertex in this case, which has not any connection to the rest of the graph. Okay, let's go further. This illustration already showed that you can look at subgraphs. So a subgraph is a graph G prime and that is a subgraph of another graph G. And it needs, well, it has the requirement that obviously the vertex set must be contained in the original vertex set V. Then also the arrow set must be contained in the original arrow set A. And then the restrictions of these mappings here must exactly be exactly according to the mappings restricted to the subsets of the subgraph. Another notion that will be important, for example, later in the discussion with respect to network theory, is to that we usually start with a finite graph. So a finite graph is one where the sets V and A are finite. Later you see when we have binary relations, it will be sufficient that only the vertex set V will be assumed to be finite, but at the moment we have no restrictions on the cardinality of either V, the vertex set, or the arrow set A, and that's why we are imposing this restriction sorry, for both of these sets. Okay, now just some further definitions, and that is about paths and connectivity. You will see this is very analogous to to basic topological features of, for example, sets in Rn. So what is a path? A path in a graph is a sequence which starts at a certain vertex V, and then it goes through a sequence of arrows from A1 to AL. V, of course, has to be in the vertex set of the graph G, and A, all the A's will be elements in the arrow set of this graph. And the requirement for a path is that then the source of the first arrow has to start at V. So this is explaining why in the definition you have this v in front of the bracket. And then you have sequentially the property that the target of the previous arrow AI is exactly the source of the next arrow AI plus 1. And this is of course for all indices going from 1 to n minus 1. So we call the path length to be L. That makes obviously sense. And then we also have to introduce loops. And a loop is a very interesting construction, because what we require here is that we have a path that goes back to its original starting vertex by going through all the different arrows. And of course it can even be that such a loop has only length 1. In this case we call it a self loop. I should just make a quick remark here, which is very, very important for us. We have already discussed feedback loops in the introduction of this course, maybe you remember, and loops will exactly be in the graph, that is representing a certain empirical system. It will be exactly it will be a structural description of the feedback loops you will see in these empirical systems. So that maybe explains why I need this definition at this point in time. With the help of the path definition, you can now define obviously connectivity. So it's clear what you have to require. You just take 2 arbitrary vertices out of the vertex set of the graph, and then if the graph is to be connected, then you require that there is a path between these 2 arbitrary selected vertices. Now, of course, this definition doesn't take into account the direction of the arrows as such. So, for example, you only require that there is a path of arrows using arrows in one direction, but you don't require in this definition that there is a backward path which also goes then from v prime to v instead of v to v prime. If you always sorry if you always have this property that the path is going from v to v prime and from v prime to v, then you would call that strongly connected. Okay, let's go to the next slide. Now I have to go to mathematical modeling. That is our aim, and so this we have to discuss. This is actually a very important discussion now, because now we are working towards what will be the variables in our mathematical models. And the best way to explain that is by introducing a classification scheme which uses types. I will illustrate that in a figure in a moment. So, as we have seen in the mathematical modeling introduction in lecture 1, every system has to be chosen to have basic objects. These basic objects are the basic components. It's what we called basic components in the empirical system. But now the basic objects are just the basic objects correspond in a mathematical theory that corresponds to basic components in the empirical system. Yeah, I think we have already discussed what the basic components of a system is. It's very much the idea that these are like atoms which cannot be further divided. So they are the basic kind of system component you can have. And now on top of these basic, all these basic all these basic components will be in a so-called black box, as we discussed it. So the black box will now be called a compartment. That's where our basic objects live. And the compartment, is the black box in the empirical system, and in the mathematical system, in the mathematical framework of graph theory, this will be called the object set, the basic object set, which we denote by capital O. The next thing is we introduce now on this set capital O of basic objects a classification which we require to be complete. So it's a covering of this set. This means every single basic object we have in our system will be exactly of one type. So the types we always denote by capital T, and we number them. In case we have, from 1 to S, so we have finitely many different types. So this is like saying, okay, we look at you look at a forest. All the basic objects are trees, and now you differentiate into species. So you have, for example, an acorn that will be T1. And then you have an oak, you have oak trees in the forest, and that will be T2, and so on and so on. So you see it's a complete classification. That means every tree you encounter in the forest will be exactly of one particular species, so exactly of one type. Okay, you can illustrate that here. So you have here this basic basic set of objects, capital O, and you have here the different types. And you see that here there's the system boundary, and so here we have in total six types, and we can skip this. And if you now associate a graph, which we will call the type graph, to this object set, that's how it works. So you have one vertex in each of the coverings that are sorting out all the basic objects of one type. So here in this case you would have all objects of type 1 would be inside exactly this region, and so on. So of course this might not be, for example, how it is in a forest. In the forest all the types would not be differentiated into one compartment, but they would be all over the place. But here we make a thought experiment. So we all we sort them into types, and they are dislocated, so to speak, in the forest to be exactly at this corner of the forest altogether. That's how you have to imagine what I was drawing here. And so here this vertex here would represent all the objects of type 2, this one every object of type 5, and so on. And the next idea we have is for this type graph is, so once you have associated one vertex to each type in the system, then we ask the question, so now which type does influence in a certain way another type. So for example, for the forest it would be like an oak tree is shading, so it would influence the growth of, for example, say the acorn, and therefore there would be let's say the acorns would be T1 and the oaks would be T2. That means we have to draw this arrow here because the oaks are influencing the acorns in their growth, and that's exactly how we get how we construct this graph. So only if we are 100% sure that there is really no influence of one species to the other, of one type to the other one, then we wouldn't draw a graph. So an example would be, for example, so here there is no direct connection between T4 and T5. Okay, now we have to go to binary relations. So let's start with introducing the binary relation. So the binary relation can be characterized as being a subset of the Cartesian product of V with itself, so V times V. And we denote the set of binary relations of SR2V. The 2 is standing for binary relation, and the reason is that we have here a Cartesian product of 2 times the vertex space. So every element in R2V here can then be later written as a 2 tuple in the usual notation. Now we introduce 2 projections of this tuple, of this 2 tuple. So we have pi1 and pi2 mapping from V times V to V. That's here. And we also introduce 1 inclusion, and that inclusion is a mapping from the set of binary relations into this Cartesian product of V with itself. We can conclude that there are 2 mappings now from the set of binary relations to the set V. So that is a mistake. That must be V. I apologize for that. And this mapping then is given by the 2 projections, which are chained with the inclusion mapping in this way and in this way. Now we can define a graph which is now based on binary relations, that is here, and this can be done in the following way. So in this construction we start again with the vertex set V as before, though this is unchained, but now instead of including here a general set of arrows, we now include here the binary relations which we have defined. And for the source and target mappings, we use here pi1 chained with I and pi2 chained with I. Now, given some general graph G, V, A, capital A, S and T as before, we can now extract a binary relation graph GR2V. Indeed, given, so let's see how that works. Indeed, given the functions, the source and target functions S and T, we can define the product function, no bracket ST, in this way, and this will be a mapping from the set of arrows into the Cartesian product of V, the vertex set with itself. Now the problem is that this is not yet necessarily a binary relation, and that is because the product function might not be injective. So you can have in the original construction of a general graph, if you go back to the definition, we can have an arbitrary number of arrows between 2 vertices. There is no restriction in the general graph, and this makes this product mapping being not injective. However, we can define now the binary relations by taking the image of this bracket mapping ST. Note that in general then the graph is different from the graph that is based on the binary relations G R2V. And that is because any multiple arrow of the original graph between two given vertices is now matched into a single arrow in this graph constructed with the help of the binary relations R2V. I think now this explains a little bit the relation between the general graph definition and the graph definition that is based on binary relations. So in the general graph, you are very flexible. You can choose the arrow set and the vertex set as you wish. If you base your graph definition on binary relations, then you are more restricted. Okay, now we can go back to the classical graph definitions, which you, I'm sure, have already heard of. So first let's go to the directed graph, which is the more immediate graph that comes out of a graph definition based on binary relations. So we have that we introduce now an arrow set A right away, and we represent the arrow as a two-tuple. So we have to pick out two vertices V, V prime in V. Now we call A the set of arrows, of course, and then we observe that it's not true in generally that this set of binary relation is ordered, is unordered. Sorry. So we don't have necessarily that V, V prime, the tuple V, V prime is equal to the tuple V prime V. And so in general they are not equal. And so they are, so this would really create two different arrows A and A prime. And if we don't require this order here, so we require that, or we assume that this is not necessarily equal, then the resulting graph will be called a directed graph. Well, this is just an illustration. Note that here I used a little bit of different notation. So this here would be, in the original notation, would correspond to something like A2. What you see here in this graph with 5 vertices and 5 arrows is that you only have here in the middle, you have something like a feedback loop. If you think about it, so in this type graph interpretation, V4 would influence V, so type T4 would influence type V1, type T1, so that is here given as the vertex V1, and the other way around. V1 is influencing then also V2. So this is usually how directed graphs are drawn, and that's how you can find them in the literature. Now let's go to another very classical definition, and that is the one for undirected graphs. Now this just uses right away, the binary relation. Here I use a little bit of different notation to make you accustomed to that. So a binary relation can also be interpreted as a mapping from the Cartesian product V times V into the number 0, 1. And you have the interpretation that if rho gets the value 0, then there is no binary relations between the elements V, V prime taken from the Cartesian product of V with itself and if the value is 1, then there is a binary relation. And because now you have that all the two tuples with taking out arbitrary pairs of vertices from the vertex set are now equal. This is why you can really now completely describe a graph with having this shorter notation where G only consists of something that, sorry, there is a G missing here, is only a graph that has two sets, incorporate the graphs of vertices and the graphs of edges. So arrows that have no clear directions are called in graph theory edges. And an illustration of that you can see in this figure. With it has 6 vertices and 7 edges, and you can see the list, the complete list to worked out here for the two tuples that define the edges in this case. Okay, now we make a jump to algebraic graph theory. This is now immensely important because we have now introduced two concepts. So we had a set theoretic construction of the graphs first, and then we had illustrations, so graph in illustration. So we were drawing graphs. We had two simple examples of a directed and an undirected graph. You can, with respect to illustrations, I should say. So in the next lecture we will have the emphasis on networks, and if you think a graph visualizing, for example, the internet, or visualizing the road network of an industrial country, then these will be immensely complicated drawings. And usually they can only be done by computers. So graph drawing is very, very important. But the problem is always, how do you actually make a computer understand what a graph is? The best way to do that is to think algebraically, because every computer language clearly can define algebraic concepts. So if we can bring if we can associate an algebraic object with a graph, then actually we are done, and then we can, for example, do graph drawings automatically. So what kind of algebraic object do we attach to the graph? This will be the adjacency matrix. So how is the adjacency matrix defined? Let's have a look. So we denote the adjacency matrix by capital A. Don't get confused in this case with the capital A we used for the arrow set before. So these are now two distinctive things, and the the adjacency matrix will be associated to a certain graph G. We assume here that the graph G has a finite cardinality. Let's say a cardinality of n in n, the natural numbers. And in this case, so that is the definition here. So the cardinality of V is n. And A then will, as we will see, A will then become a matrix with n rows and n columns, defined as follows. So it will be a matrix where each entry Aij of the matrix only is either a 0 or a 1, and Aij will have the value 1 if the tuple Vi of Vi and Vj, so Vi and Vj are two chosen vertices in the vertex set V, if this is a binary relation, so if that exists, and it will be 0 if it doesn't exist, if it's not a binary relation. Okay, so this is the adjacency matrix, and the adjacency matrix is symmetric in case the graph is unordered, and if it's a directed graph, so the binary relations are ordered, then the adjacency matrix is not necessarily symmetric. Yeah, and please look at some examples you make up for yourself. Okay, let's go further. Now we can introduce a so-called spectrum of the adjacency matrix. So the spectrum of G is a set of numbers which are the eigenvalues of the adjacency matrix together with their multiplicities as eigenvalues of A. We can order these distinct eigenvalues by magnitude. That is what we did here, and we have s-1 many of them, and we can associate to each of these eigenvalues their multiplicities, m of 0, 1, m of lambda 1, and so on up to m of lambda s-1. And then the spectrum of G, of the graph G, is the spectrum of the adjacency matrix associated to G. So you have here a scheme where in the top row you write down the A eigenvalues, and then in the lower row you write down their multiplicities. Here I have an example. So this is the spectrum of K4, and it turns out to be like this. And this you should check yourself as an exercise. Now there is an interesting theorem, and this shows you the full power of algebraic graph theory. And yeah, first let's define the characteristic polynomial chi of G and lambda, and this is of course the determinant of the adjacency matrix minus lambda times the identity. And we use this form, this normalization of the characteristic polynomial chi. And then the coefficients ci of this characteristic polynomial can be interpreted as follows. And this is quite interesting. So we have that in this case, the first coefficient c1, which was here, is always 0. Then minus c2 is the number of edges of G. Now, you know, this can also be interpreted as the following way. So, you know, one edge together with the two vertices which are connected by this edge. This is of course also a subgraph in our notation, or in our definition. So this would be a very small subgraph with two vertices and one edge. And so minus C2 would be the number of these very simple subgraphs. And now minus C3 is twice the number of triangles in G. So these are a little bit more complex subgraphs of G, which look like that. So you have 3 vertices taken out of the vertex at V, and they are connected by 3 vertices. And this is a complete graph in the language of graph theory. And yeah, as we will see later, some construction like that will also be called a motive in network theory. So this is a very small kind of graph. And for example, an interesting question then is, how often does a triangle occur in a certain network, and things like that. And you can see in this theorem, which is quite interesting, that that you can actually compute the number of such triangles, so of the complete subgraph, which is called usually K3, purely algebraically. from the characteristic polynomial. So this is quite interesting. I just quickly go through the proof. You can you can recapture that for yourself mostly. So the thing is that this part of the theorem which states that C1 is equal to 0 is easy to explain because the diagonal elements of A are all 0. We assumed here that the graph was an undirected graph and it had no self loops. So no self loops means exactly that the diagonal of A is of 0, and this makes C1 clearly 0. Now, in case of the number of edges, you have to see that an edge is connected to the principal minors of this form. So you have here, the determinant of the submatrix 0, 1, 1, 0, and so for each pair of adjacent vertices of G, there is one such minor, so-called minor, and each of one has the value -1. This means that -1 to the power 2 times this coefficient C2 is exactly minus times the number of edges, which is here notated in this way. Now let's go to the triangles. The triangles are associated with minors which are which are then submatrices, 3 times 3 submatrices, so 3 columns, 3 rows, and the combinatorial possibilities where you add a triangle to the summation. It can only be of this form, or this form, and only the last one, so this one, contributes actually a value of 2 to this coefficient, and that exactly gives you the conclusion of the proof, how many triangles there are in this graph represented by the adjacency matrix. Now I go to a very important subject for mathematical modeling. This is the subject of weighted graphs. Yeah, so weighted graphs in graph theory don't play they don't play a big role, or they play surprisingly small role. But if you want to apply graph theory to real world phenomenon, actually you always end up with a weighted graph. So people who do applications of graph theory to the real world, for example, contact graphs in epidemiology, they should always be weighted. So what is the intuitive idea? So let's, for example, think of a contact graph in epidemiology. You draw an edge of if one person, so every person is represented by exactly one vertex in this contact graph, and you would draw an edge between the two persons if they potentially can infect each other. And if you have this concept of the contact graph, then it's clear, people can of course infect other people, but it will depend very much on the situation, on many background information, how close or how easy it will be for one person to infect the other. So there is no universal binary relation that says, I always infect you with the same probability, but this probability will vary. And if it varies, then this will get rise to a contact graph which is weighted. It should be weighted by, for example, the probability that one person can infect the other one. So this maybe explains you why we have to look at weighted graphs. So weighted graphs can be very easily can be easily represented by two functions. So they are here denoted by f subscript v and f subscript a. So one is a function that maps the vertices to a so-called record set Rv. So Rv is a record set which in the simplest case would be, for example, just the real numbers. If it's about, for example, the probability of something or some characterization of something of the vertex that can be characterized by just a single real value. In case it must be characterized by more than a single real value, then you would have to introduce a Cartesian product for the choice of this record set Rv. Now you can, of course, not only weight vertices in the graph, you can also weight the arrows in the graph. In this case, you have to choose yet another record set Ra, but this goes completely analogous to the record set Rv. So Ra contains all the information you need to weight arrows. And both Fv and Fa are called weight functions. Now it's best to go through a number of simple examples to illustrate better weighted graphs. Now the easiest example, which you guess you all have in your mind, for example, when you have a car and you have a GPS satellite navigation system, then you know exactly what I mean. So the road network very let's say naturally is a weighted graph. So why? Well, first of all, let's look how the road network is constructed. Well, the vertices here are representing, let's say, villages and towns, and an edge is drawn there if there is a road connecting them, the two. Now, what would be good weights for villages, towns, and roads? Well, for example, for roads, it should be something like the length of the road. But that would be indeed, let's say, a real number. Depending, the number would, of course, be different according to the unit you take, let's say miles or kilometers. But there might also be more information you want to weight the roads with. Just think of it a little bit. So, for example, you would like to know if this is a big road or a small road. So, for example, does it have only one lane, or is it a motorway having 2 or 3 lanes? This information could also be put into the record set. In this case, if you have the length of the road and the length of the road and the number of lanes of the road, and this record set would be something like the Cartesian product of R times the set 1 from 1 to 3, which is the number of lanes. And what would be a good weight of the villages and towns? Well, you can, for example, just take the number of inhabitants. This would give you a lot of information, for example, how busy the roads are, because the number of inhabitants will be proportional at least at some times, to the usage of roads connected to it. Another very important scientific example will be protein-protein interaction, so-called PPI networks. So here the vertices are proteins, let's say from, extracted from a certain organism. So you can extract a PPI network for each organism you have, in this case of all the cells together, or you can also have PPI networks associated to just a single cell. But you can imagine experimentally this is much harder to achieve. Yeah, so it's clear the proteins would be the ones giving rise to the choice of vertices. But then the question is, what is actually defining the arrows or edges, in this case edges, in the graph, and that it would be, for example, the binding strength of the two proteins. So yeah, and binding strength, that's also important to note in this example, is of course an unordered relation, because if a protein A binds to a protein B, then also the protein B binds to protein A. So you don't need to introduce arrows. You can really model this PPI network by an undirected graph. Okay, and then the next question is there a useful weight for the proteins themselves, so which are representing the edges of this undirected graph? The answer is yes. It would, for example, be the size of the proteins. That is usually measured for the ones interested in kilodaltons. Okay, this brings me to the end of this lecture. Let's go through the summary as usual. So we learned about basic graph definitions. We discussed how graphs are used in mathematical models. Remember, here we introduced a classification scheme based on types. This will be a topic that runs through the whole lecture from the beginning to the end. So please make yourself familiar with this concept. Then we also introduced classical graph concepts, which are all based on binary relations. And then we had a journey into graph theory, algebraic graph theory. This is very important. The major example is that you have the ability with algebraic graph theory to bring graphs into a computer and make calculations of properties of the graph or make drawings of the graph. And then we introduced a very, very important concept of weighted graphs for mathematical modeling and structural modeling, which we are doing at the moment here. Weighted graphs are really essential. You should always be suspicious if you find unweighted graphs in applications. So for graph theory, they are, it's a mathematical object. Unweighted graphs are fine, but it's hard not to see for any applications why not additional information should go into the graph description, into the structural description. So you will nearly always encounter weighted graphs. Well, this brings the lecture to an end, and yeah, I say goodbye.